Scientist focused on quantum computation. And I first met Juan Maldacena 14 years ago when I was a member here at IAS in Avi Vigderson's group in the School of Mathematics. And I remember I made an appointment with Juan to ask whether he thought that if we took the as given that certain computations required exponential time in our universe, that would have any implications for the black hole information problem, especially in the context of his proposal with Horowitz about a final state projection or quantum gravity more generally. And I remember that Juan listened extremely politely. He is extremely polite, but it was a little bit like maybe if the anteaters went on a trading mission to the beluga whales, and you might imagine that the beluga whales would say, "Well, thanks. We'll let you know if we need any ants, but we're doing okay as it is." So it's been exciting for me, as you can imagine, to watch quantum gravity and quantum fields and quantum information actually come together over the last 5 or 6 years with this IT from Qubit collaboration, and to be, I guess, peripherally involved as sort of an unofficial CS consultant. Today, all of my interactions with Lenny Susskind involve me saying, slow down, Lenny. Computational complexity could be a useful tool or diagnostic for certain things, but it's not like this is the future of all of physics. And then he responds, "It absolutely is, and everyone should be working on this." So in these talks, I'm going to be less evangelistic than probably Lenny will. Well, you'll hear him yourself next week. I want to try to explain how computational complexity has been used as a tool in, for example, Harlow and Hayden's beautiful work on the firewall problem. Also, the way that Lenny and I and others have used it to understand some aspects of AdS CFT and the thermofield double state. I'll let you draw your own conclusions about how useful, how fundamental it is. But hopefully these talks will help you to evaluate appeals to computational difficulty when they're made in this field. Maybe even make such appeals yourself, should you wish to. To that end, I will give lots of exercises and even mention some of my favorite open problems. Okay, so I'm going to define circuit complexity formally before long, but very roughly speaking, by the circuit complexity of a unitary transformation, let's say acting on n qubits, we mean something like the minimum number of elementary quantum operations. Let's say, for example, unitaries acting on only 1 or 2 qubits at a time that would be needed in any circuit that implemented that unitary transformation, right? You can always take a complicated unitary acting on a tensor product of many two-dimensional systems, and you can always decompose it as a product of sort of small operations that act on only a few qubits at a time. We're interested in how many small operations you need. Okay, likewise, by the circuit complexity of an n-qubit quantum state, we would mean something like the minimum number of elementary unitary operations needed to prepare that state, starting from some canonical initial state, such as the all-zero state. Okay, but stepping back, why would anyone imagine that this sort of measure would be relevant to quantum gravity or fundamental physics, right? It sounds kind of messy. One thing that Lenny likes to do is to stress an analogy to thermodynamics. So if we consider the entropy of a probability distribution, the Shannon entropy, or the von Neumann entropy of a quantum state, right? These are not quantities that appear anywhere in the fundamental Lagrangian. And yet, Nadi Seiberg and I were just discussing this a few days ago. Entropy and relative entropy and other information theoretic concepts turn out to be so important for physics that you might say that, once Claude Shannon introduced these concepts in 1948, they already started revolutionizing physics by negative 100 years afterward. Okay, so why is entropy so important for physics? One possible answer to that question is that entropy it can be needed to break symmetries, or what would look like symmetries in the fundamental equations. So most famously, there's the symmetry between scrambling an egg and unscrambling it, or between rolling a ball up a hill and rolling it down, right? Entropy lets you articulate formally why it is that a physical transformation can be so much easier in one direction than in the reverse direction, even if the equations appear to treat them symmetrically. So a point of view that I'm going to advocate in these talks is that circuit complexity can play a similar role of breaking symmetries. For example, as far as the axioms of quantum mechanics are concerned, every unitary transformation that you could perform on a collection of qubits in your possession seems to be on the same footing with every other unitary transformation. Likewise, every orthonormal basis in which you could measure those qubits seems to be on the same footing with every other orthonormal basis. Okay, and of course we all know that in practice, some measurements are easier to perform than others. Some unitaries are easier to apply than others, right? Certainly any experimentalist knows that. But we don't always think of that as belonging to the formal part of quantum mechanics, right? You could say that's just sort of an engineering issue. So I think where circuit or computational complexity rear their head is when you do want to articulate a formal sense in which some measurements, some unitary transformations, or some states are accessible to you, whereas others are astronomically inaccessible, so to speak. Okay, so to take one example, let's start with a fundamental fact that I guess Edward explained in his lecture on Monday morning, the symmetry of conditional entropies or conditional information, right? H of x given y is equal to h of y given x for any two random variables, x and y, right? The amount that you're uncertain about one given the other is symmetric. Okay, so let's take a particular instance of that. Let p and q be two enormous randomly chosen prime numbers. Let's say with thousands of digits each. Let n be their product. Then the entropy of n given p and q is equal to the entropy of p and q given n. In fact, they're both 0 in this case. We would say that giving the composite number or giving the prime factors, is informationally equivalent, right? Tells you exactly the same amount. Okay, and yet, to go from p and q to the product is quite easy, at least if you have a computer. To go from the product to the prime factors, famously, let's say using any known method on any currently existing computer, could easily take you longer than the age of the universe. Okay, so somehow there's a sense in which computational difficulty at least appears to break this symmetry. Okay, and as many of you might know, famously, this sort of asymmetry between say going in one direction and going the other. In some cases, this particular asymmetry between multiplying and factoring is at the core of how modern cryptography works. Okay, yes?
This implies h of x equals h of y?
H of x, sorry, say that again?
Doesn't this imply h of
Does it imply h of y equals h of x? Mutual information, yeah. So wait, so what do I have to fix?
H becomes an I.
Oh, all right, fine. So I just, okay. Okay, is that right? All right. So, okay, so to be a little bit more formal, the sort of central object that's used in modern cryptography is known as a one-way function. Okay, and this is or ALF. Okay, so this is defined as a function f, really a family of functions. Let's say, parameterized by n, maybe with some additional parameter as well. But each function in the family, which I'll just call f for simplicity, is going to map an n-bit input string to an m-bit output string, where m, let's say, is could be some multiple of n, could be n squared, but it's something, let's say, polynomially related to n. Okay, and a one-way function has to satisfy two properties. First of all, it has to be easy to compute in the forward direction. Okay, and our rough and ready criterion in computer science for easy to compute is computable in polynomial time, which means by some algorithm that uses a number of steps that grow, that can be upper bounded by some polynomial in n, right? And of course, we know perfectly well that this is an imperfect criterion. For example, if you had an n to the 10,000 power algorithm, that's not very good. And conversely, we tend to think of exponential as being inefficient. Of course, if you had a 1.000001 to the n algorithm, then that's preferable to n to the 10,000 in practice. However, those sorts of cases tend to arise more rarely. So you might say that if we can't even figure out what is computable in polynomial time and what requires exponential time, then surely we're not going to answer the more refined questions either. So we might as well focus on polynomial time as a start. Okay, so so a one-way function should be efficiently computable, but it should also be hard to invert, in the sense that if I pick a random input string x, and then I just tell you y equals f of x, then it should be difficult for any polynomial time algorithm to find any preimage of y, okay, which might not necessarily be x itself if f is not injective. Okay, meaning that any such algorithm, should have a very small probability of successfully outputting a preimage. Ideally, its success probability should be, let's say, at most 1 over an exponential of n, the same as you would get just by randomly guessing a preimage, which, of course, you can always do. Okay, but at any rate, the success probability should be less than 1 over any polynomial in n. Okay, so a sequence of fundamental results in the 80s and 90s showed that given solely the assumption that there is such a one-way function, which remains an unproved assumption, as we'll come back to, but solely given that assumption, one can build much of what is needed to do modern cryptography. Not all of it, but a lot of it. On the other hand, for many cryptographic applications, one needs special types of one-way or one-way functions with additional properties. Okay, of particular relevance for this talk, sometimes we need one-way functions that are injective. That's not a very stringent additional requirement, right? If we just take the output to be long enough, like, so let's say 3n bits or 10n bits, and we take something that's sort of sufficiently scrambling, then, we might expect that with high probability, we will sort of avoid the birthday paradox. That is, sort of avoid collisions and, cause our function to be injective. Even better would be if we could take m to equal n and just have an injective function from n bits to n bits. This, if it exists, we call a one-way permutation. Okay, and then to actually do cryptography over the internet, we typically want something called public key cryptography, right, where we can exchange secret messages without having to agree on any key in advance. Now, if you want that, then you need something stronger than just a one-way function, which we call a trapdoor one-way function. Okay, and these trapdoor one-way functions tend to be much more special. They tend to be based on specific, problems coming from number theory or group theory or elliptic curves that have some mathematical structure to them. And what these let you do is these are one-way functions with the additional property that if I give you some secret trapdoor information, then the function becomes easy to invert, right? So these are functions that are easy to compute, difficult to invert, but that become easy to invert again, given some secret trapdoor information. Okay, and these are the basis for, in some sense, for almost all of the cryptography that we use with our web browsers. Things like RSA, Diffie-Hellman, elliptic curve cryptography. These are all based more or less on these trapdoor one-way functions. Okay, so. Okay, good. So you might wonder, won't quantum computers completely change this situation once we get them, right? You've probably heard of Shor's famous quantum algorithm for factoring integers in polynomial time with a quantum computer. And we could say that in this specific case, of this asymmetry between, a composite number and its prime factors that we had for classical computation, in some sense, Shor's factoring algorithm restores the symmetry, right? It makes, at least if you were able to build a scalable quantum computer, then he shows that then factoring is not much harder than multiplying, okay, remarkably. And this famously got lots of people interested in quantum computing in 1994 because, it showed that, a quantum computer has some application besides simulating quantum physics and chemistry themselves, which was the original application that Richard Feynman had in mind. Of course, breaking cryptography, it's not clear that that's a positive application for humanity because it depends on who's doing it, to whom. Some people have the impression that Shor's algorithm does more than it does. So to state the situation as we understand it today, what a quantum computer would do, well, first of all, it could invert every known one-way permutation. Okay, so we do not have any candidate for a one-way permutation that would be secure against quantum attack. All the candidates we have are based on things like discrete logarithms, which some variant of Shor's algorithm is able to handle. In addition, let me just write QC here. Quantum computers are known to be able to break as it happens, almost all of the public key cryptography that we currently use to secure the internet. Okay, so that includes RSA, Diffie-Hellman, elliptic curve cryptography, and more. Okay, however, even if we want public key cryptography, there are public key crypto systems under development, most famously systems based on the hardness of finding short non-zero vectors and lattices that we currently don't know how to break, even using a quantum computer. Okay, so these crypto systems would be very clear candidates, in a world where scalable quantum computers look to be on the horizon, that we could use instead. They would work over the existing internet, so we wouldn't need a quantum cryptography or anything like that. And as far as we know, even a quantum computer would not be able to efficiently invert the underlying trapdoor one-way functions. Okay, but now, more relevantly for this talk, if you only want a one-way function itself, or an injective one-way function, which are the things used to do private key cryptography, where you and your friend can meet in an alleyway at 2 a.m. to agree on the secret key, right? If you only want the general one-way functions, then we have many, many candidates that we have no idea how to break, even with a quantum computer. Okay, so what you can do, for example, is just take some, any sort of transformation that you can imagine that would sort of sufficiently scramble up your data. For example, feed it into some deterministic cellular automaton or something of that kind. Take that transformation and iterate it 1,000 times, let's say. And then you'll typically get something for which we don't know, even with a quantum computer, how to do that much better than brute force search. Okay, what you can always do with a quantum computer is something called Grover's search algorithm. Now, what Grover's algorithm does is that if I had any kind of space of n possible solutions, or here I should think of n as being exponentially large, a quantum computer can search that space in only about the square root of n steps, compared to n that would be needed for classical brute force search. Okay, so that's impressive, but that's not an exponential speedup, right? It is merely, quote unquote, a quadratic speedup. So what Grover's algorithm would mean in practice is that with these one-way functions, or with the crypto systems that are built around them, if you wanted the same level of security that you had before in a world with quantum computers, you could achieve that by roughly doubling the length of your secret key, right? Thereby squaring the number of possible keys. Okay, so indeed, later in this talk, we will use the assumption that there are injective one-way functions that are hard to invert even using a quantum computer. Okay, and what I wanted to impress on you is that, by the standards of computational complexity, this is considered a very, very generic, very safe assumption. We have much more dangerous ones, if you prefer. Okay, so, okay. So now we're now in a position to pose a puzzle to, let's say, to check your understanding. So, a fundamental result from the 70s and 80s from the work of Bennett and Benioff, Feynman, Toffoli, Fredkin, is that any digital computation whatsoever can be simulated by a reversible computation. Right? A computation, the computation can proceed in such a way that every step is reversible, is unitary, for example. Okay, this, this was one of the first questions, people asked about quantum computation. Before asking whether quantum computers could do anything faster, they asked, can a quantum computer at least simulate a classical computer without a slowdown? Can you use the space shuttle to taxi around a parking lot, if you like? And so the answer turned out to be yes. We can take any computation and we can make it reversible with low overhead. Okay, but now my puzzle is, if that is so, then how could any one-way functions possibly exist? Okay, because after all, if I had a reversible operation that could map x, say padded out with some zeros, to f of x, then by simply applying the inverse of that transformation, just inverting each of my operations and reversing their order, I could also map f of x back to x, right? So how could you have one-way functions if all computation can be made reversible? Does anyone know? Yeah.
Project at the end to some, after doing computation, project to some subspace of the results?
Well, but this if we did the computation like this, we wouldn't need any projection. Finding the inverse is hard, right? But if we write it like this, it looks like finding the inverse is quite easy, right? Because if f, if f were not injective, then what I wrote would not even make sense. But assume that f is injective, right? Excuse me?
Do you have some fundamental gates for the classical version, and then show that you can kind of group invertible ones
Well, yeah. We do need some transformation that will take any computation, possibly an irreversible one, and will make it reversible. Okay. So the key to resolving this mini paradox, if you like, has to do with what happens when you perform that transformation. Okay. And the answer is interesting. Let me. So. What happens is that we can take any efficient algorithm to compute f, and we can get from it a reversible transformation, call it C, such that when we apply C to x, together with some answer register, as we call it, padded out with zeros, then f of x gets written into the answer register. Okay? This one can do. I'll leave it as an exercise to show, if I had an ordinary Boolean circuit made of and, or, and not gates, let's say, that computed f, then give me a circuit that acts reversibly, that just consists of a bunch of, invertible operations that will have this effect on x together with all zeros. Okay, that was a pretty famous result, but once it's stated, I think that any of you could prove it tonight. Okay, so but now notice that x is still sticking around here. Okay, and the fact that x is still around is what makes this useless for actually inverting f. Okay, so so if you like, all of the difficulty in the reversible computation is not in computing f; it's in getting rid of x. Okay, so indeed, if we could. Indeed, if we could map x to f of x, then we could also map f of x to x. Okay, but typically we can only do this. Okay, and that is how one-way functions can exist, even in a world where all computation can be made reversible. Okay, but so now you may say, well, these one-way functions sound great, so let's just are you going to prove that they exist? Okay, well now I have to I hope you're sitting down for this. I see most of you are, but proving the existence of one-way functions takes us directly into some of the deepest open problems of modern mathematics. Along with the Yang-Mills mass gap and so forth. One of the Clay millennium problems is this P versus NP problem that you may have heard of, and we're now knocking on its door. Okay, so, yeah, question?
I have a question. The special class of one-way functions?
Yes.
Do they preserve entropy?
Which ones? The one-way permutations, or?
The ones which...
Over here? Do you mean, I'm sorry, do you mean these?
Yeah.
So these would actually not be one way by the very fact that they can be computed in this way, right? That then demonstrates that these are not one-way functions. Right, because, here's how to invert the thing. Right? Indeed, this argument was correct, but it's just that typically when making a computation reversible, the original input x still stays around. That's the issue. Yes?
Another way of saying what you just said, you have some scratch space when you do a computation, and the scratch space at the end, you have something that depends on x.
Yes, that is absolutely true, right? And in fact, if you just do the computation naively, what I predict you'll find is that, given x, you can compute x and f of x and a whole bunch of additional bits that were just your work as you did the computation. Okay, the technical term for this is garbage. Okay, although it's not. I mean, it's not exactly garbage because it's what you needed to do the calculation. Okay, but very often in quantum computation you then need to get rid of it because it's going to be blocking interference between two basis states, for example. Okay, so part of doing this exercise is going to be figure out how to get rid of the garbage, thereby leaving only x and f of x. Okay, you still can't get rid of x, but at least you can get rid of the additional garbage. Okay, so in asking do one-way functions exist or do they not, we're led to yeah.
Simple question.
Sure.
So here you are saying getting rid of x means like I cannot simply read it from the right-hand side what x is. You want to encode the x in some complicated way, I cannot read it easily.
Well, you could do something to scramble x up in some way, right? You could sort of try to make it, although if I do a known reversible circuit and it acts only on x, then someone could always unscramble whatever I did. How?
Oh, yeah.
By simply inverting that circuit, right?
So what do you mean by getting rid of?
I mean just having f of x only in your register. Okay, that is the thing that is hard to do here. Precisely because if you could do it, then you could also invert f. Okay? Yeah?
Does that mean that even getting f of x is difficult? Even compute f of x is difficult to get the result?
Well, no, because by the assumption that f is easy to compute, as I said, you can map x comma zeros to x comma f of x. Okay, so that you can do, right? It's just getting rid of x that's the hard part.
But how to read the f of x from the final?
Oh, well now you can just, I'll assume some facility to measure your qubits, right? If you're building a quantum computer, let's say, you better have the ability to measure a qubit and see whether it's 0 or 1. Okay, so I'll assume that ability. Yeah?
When you say difficult, you just mean that you increase the entropy by trying to erase it by somehow interacting only with the first qubit and making it so.
Yeah, well, I mean, if we could just throw x into a garbage can, or let's say throw it into a black hole if we believed that they were information erasing, which maybe we don't. Okay, but in any case, that would not be a reversible transformation. That would not be unitary. Yeah. Well, I'm about to get to that. Yeah, I mean briefly, whatever size circuit we need to compute f in the ordinary non-reversible world, I'm asking you to, in this exercise, to show that the circuit complexity of applying this transformation is not much greater. Yeah. Yeah. Right. Uh-huh. Yes, that's correct. That's correct. Okay. So just to briefly orient you in sort of the universe of classes of computational problems, I won't spend too much time on this, but the most basic sort of class of problems that we study in theoretical computer science is called P for polynomial time. It is the class of all of the decision problems, that are solvable by some polynomial time algorithm running on a standard, deterministic digital computer like the one in your pocket. Okay, so an example of a problem in P would be I give you some encoding of a graph, and I ask, is the graph connected or not? Okay, or I give you a positive integer written in binary. I ask you, is it prime or composite? Okay, that's a famous one. That was only proven to be in P in 2002. Okay, now crucially, the algorithm does not tell you what the prime factors are in the case that the number is composite. That as far as we know, is a much harder problem or requires a quantum computer. Okay, but now there's a small generalization of P, which we call BPP, or bounded error probabilistic polynomial time. This is informally the class of all the decision problems that are solvable using a randomized algorithm, a probabilistic algorithm that runs in polynomial time. And for every input is required to output the correct answer with some probability that is bounded above a half, like let's say 2/3. Okay, why is a 2/3 probability of the right answer good enough? Can anyone answer that? Excuse me, yeah, because if we don't like it, we can just run the algorithm over and over and then output the majority vote. Okay, that's called amplification. Okay, but now fundamental discoveries, in the 1990s due to Impagliazzo, Wigderson, Nissan, and others convinced most of our community that ultimately BPP should actually be equal to ordinary P. And the reason is that this is now known to follow if you can build good enough pseudo-random generators, right, which you could then feed to your randomized algorithm in place of truly random bits. And furthermore, it is known that under very, very mild computational assumptions, still beyond what we can prove, but very mild looking, one can indeed construct the requisite pseudo-random generators. Okay, so I'm just going to put this as probably equal to P. Okay, as we know, when we come to quantum computation, the situation will be different. There, we don't, most of us don't think that is equal to classical P. Okay, now NP stands for non-deterministic polynomial time. I apologize, you guys are just better at naming things than we are. Okay, but quark, string, right? We're stuck with. Okay, but. But NP, informally, is the class of all of the decision problems where if the answer is yes, then there is a short witness, meaning like some polynomial size string that if it is given to you allows you to verify in polynomial time that indeed the answer is yes. Okay, crucially, it might be very, very hard for you to find that witness on your own, okay, if it weren't given to you. Okay, so it will help to give an example. A good example of a problem in NP, would be factoring. Or let's say some decision problem based on factoring, such as I give you an integer encoded in binary, and I ask, does it have at least 3 distinct prime factors? Okay, now crucially, if the answer is yes, then you can easily prove that to someone by showing them the factors, okay? And then, they can check that they're prime, as we discussed. They can check that they are indeed factors, okay? But finding them for yourself might be much, much harder, okay? Almost every optimization problem and constraint satisfaction problem that arises in science and industry falls into this class NP, or at least can be phrased as an NP problem. For example, if we had an optimization problem, to say optimize some flight schedule, then we could simply ask, well, is there a schedule whose total cost is at most k for some given k? Okay, and then given the ability to solve that problem, we could then do a binary search over the possible values of k to find to know what is the optimal schedule. Okay, now what if you additionally wanted to find the schedule beyond just knowing that it exists? Well, I'll leave that as an exercise for you. Show that you could do that as well. Okay, so, now also relevant for me later will be a class called PP, probabilistic polynomial time. This is all the problems that are solvable by a randomized algorithm that now merely has to guess the correct answer with some probability greater than a half. Okay, it could be a half plus 2 to the minus n. That's fine. Right? It could be super duper close to a half. Just has to be more likely to guess the right answer than the wrong one. Okay, so that's a powerful class. It contains NP. Let me come back to this. And then above that, we have PSPACE, which is the class of all the decision problems that are solvable by an algorithm that uses only a polynomial in n amount of memory, okay, but possibly in exponential time. It could use the same memory over and over. Okay, and by the way, I should say, for each of these, right, these are classes of problems. A problem is just like an infinite collection of instances, right? Each, like for example, if I give you a particular number and I ask you to factor it, that's merely an instance. Okay, it's not until we consider the set of all numbers to be factored that we would say, well, there's a problem. Okay, and and when we say polynomial time, we mean using an amount of time that grows only the number of bits of the instance raised to some fixed power. Okay, so above PSPACE we have exp, which is the set of all the problems that can be decision problems that are solvable in exponential time. Exponential here meaning any running time of the form 2 to some polynomial in n. Okay, okay, and then here off to the side I have BQP, which stands for bounded error quantum polynomial time. And this is sort of the quantum computing generalization of the class P. This is the class of all the decision problems that are solvable in polynomial time by a quantum computer, with some success probability on every instance, which is bounded above a half. Okay, and Shor's algorithm shows, for example, that factoring is in BQP, although it's not known to be in P. Okay, and BQP is known to be in PP, and hence PSPACE, right? So, it can be fit into this hierarchy, but, it's a little bit off to the side. We don't know the relationship between BQP and NP. It's thought that perhaps they are incomparable. Okay, yeah?
Is there some classification of physical processes which are in class P?
Oh, well, in fact, we're going to come to that shortly. I'm going to start talking about the complexity of preparing a state or applying a unitary transformation, and how those sorts of questions, relate to these classes that are sort of more traditionally considered in computer science. Yeah.
So is X the top?
Yeah, that's supposed to be containing PSPACE. Okay, I could give it as another exercise for you. Prove the inclusions that are in this diagram. Okay, in particular, prove that PSPACE is contained in exp. I'll give you a hint for physicists: Poincare recurrence. Okay. Oh no, you could keep going, limited only by how much board space there is. I mean, we could have doubly exponential time, like 2 to the 2 to the n time. We could have doubly exponential space, and so on forever, right? And then towering above all of them would be the halting problem, things that are literally not even computable, right? But one thing we know is, for given any computational problem, we can define a harder problem. Right, so there's no limit to hardness. Okay, but mostly we like to sort of stay inside of this realm because this already contains problems that are plenty hard enough. Okay. So a result that I proved in 2004 was that this class PP, of like problems where you can guess the answer with probability more than a half, is actually precisely equal to what you could do in polynomial time with a quantum computer if you had the additional ability of post-selection. Okay, which means that you could measure a qubit, let's say in the 0-1 basis, and just assume that the outcome will be 1. Okay, even if that is exponentially unlikely to occur, you can just project onto the 1 outcome. right? And just, assume that that happens, right? So that would be clearly a very powerful ability if you had it, right? You could just, sort of go into a superposition over all possible answers to your hard problem, set some control qubit to be 1 if and only if you found the right answer, and then just condition on that qubit being 1, right? That would be awesome if you could do that, okay? So indeed, this quantum computing with post-selection, lets you solve all the NP problems. But it's even more than that. Okay, we've seen that post-selection is very powerful, right? The Ree-Schleider theorem says you can even create Jupiter somewhere else by post-selecting on the outcome of some measurement over here. What I showed is that if you combine quantum computing plus post-selection, then you get exactly the problems in PP. That will come up in tomorrow's lecture. Okay, but now what can we prove about this picture? Well, you've probably heard that we can't prove that P is different from NP. In fact, it is worse than that. We cannot even prove that P is different from PSPACE. Okay, so, for all that can be rigorously proven, this could all come crashing down to P, except we can prove that P is different from exp. Okay, so at least there's that. So the way that one proves that, I won't have time to do it, but if you've seen the Turing's proof of the unsolvability of the halting problem, it is sort of a scaled down version of that proof. It relies on diagonalization. Okay, and you can similarly show that more is computable in n cubed time than is computable in n squared time, for example. More of the same resource lets you do more. Okay, comparing different resources is a much, much harder affair. But from the fact that P is different from exp, we can conclude, for example, that either P is different from NP, or NP is different from PP, or PP is different from PSPACE, or PSPACE is different than exp. The common opinion would be that all 4 of those are true. Okay, but we know at least one holds. Okay, so where do one-way functions fit in here? Well, I'll put them a little bit below NP. Okay, certainly, if P were equal to NP, then there could be no one-way functions. Right? So this explains why we sort of cannot unconditionally prove their existence. Okay, now because inverting a one-way function is a perfect example of an NP question, right? It's easy to check the answer once if someone does it. Okay, now a question, yeah.
So right now in practice we even don't know any one-way function.
Oh, we have many, many candidate one-way functions. Okay, it's just that for none of them has it been, unconditionally proven that it's one way. Okay, and it can't be unless one first proves P is not equal to NP. Okay, now going in the converse direction has actually been an open problem for 40 years. Could one show that one-way functions exist under the sole assumption that P is not equal to NP? Okay, let me give that as an exercise, but if anyone can do it, then come talk to me. or to Avi. Okay, with a question.
So quantum computing does not make any non-computable problem into a computer.
That's exactly right. Yeah, and that's a very important point that was realized early on, right? Because BQP is contained in exp, we conclude that a quantum computer cannot take anything that is literally uncomputable and make it computable. It could at most give you an exponential speedup over what you could do classically, right? Which of course is impressive enough as it is. But furthermore, in our current state of knowledge, we can't even hope to prove unconditionally that quantum computers do give that exponential advantage. Why? Because BQP is sandwiched between P and PSPACE, right? And if P were equal to PSPACE, then there wouldn't be any point in building a quantum computer. But then I think we'd be happy enough about our newfound computational superpowers that we wouldn't care. Okay, so. Yeah.
Do you have something like Qx?
Oh, sure. You can define any of those things. You could have quantum exponential time. As I said, you can continue this hierarchy as far up as you like, limited only by your patience. Okay. So let me now discuss quantum circuits. I think I even, there you go. Okay, so, you know, as I said, one can think of classical computation as just, you know, a circuit, say a sequence of simple Boolean logic gates, such as and, or, and not, right? And then very, very roughly, the class P would correspond to those collections of Boolean functions that are computable by a family of circuits where, you know, the circuit for the functions with n inputs would have size polynomial in n. Okay, now I say roughly because in order to put a problem in P, there is one additional constraint it has to satisfy, and that is that the circuits themselves have to be findable efficiently. Right? So there has to be like an overall, you know, efficient algorithm, let's say a Turing machine, that is able, given n as input, to output a description of the nth circuit in time polynomial in n. Okay, that requirement is called uniformity, that there be a single algorithm that work for any n. If we remove the requirement of uniformity, then we get a class called P/poly. P with polynomial size advice, which I'll say more about tomorrow. Okay, but this is where we would allow an infinite sequence of polynomial size circuits where it could be a completely different circuit for every value of n. That would be allowed. Okay, let me give you one more exercise. Prove that P/poly is strictly larger than P. Okay, and in fact, it contains problems that are not in any of the other classes that I showed. Okay, in fact, just to give you a hint, prove something stronger, that whereas all these other classes contain only a countable infinity of problems, P/poly contains an uncountable infinity of problems. Okay, okay, and yet, despite that, you know, in practice, the, you know, uniformity often doesn't make much difference. Okay, so certainly when we come to quantum computation, circuits are, you know, the sort of most convenient way to think about what's going on. Right? Typically, we think about a quantum algorithm as a classical algorithm that, given some n as input, let's say the size of our problem or the number of qubits that we'll be working with, then outputs a description of a quantum circuit, you know, acting on those n qubits, and which consists of a polynomial in n number of elementary quantum operations or quantum gates. So this is theoretically convenient. It also corresponds fairly well to how a quantum computer would work in practice. Right? If you walk into a lab, you'll mostly see students sitting at their classical computers, just you know, programming them to figure out, you know, how to aim the laser into the ion trap or whatever it is. Okay, so. A little more formally, a quantum circuit, let's say C, consists of a sequence of unitary transformations, each of which acts on only a small number of qubits, let's say for convenience 1 or 2 qubits, and so is the tensor product of a unitary on those qubits with the identity on all of the remaining qubits that are not being acted on. Okay, so the state of our system at any point in time, I'll take it to be a pure state for simplicity, call it psi, is an element of C2 tensor n. So it's a unit vector in a 2 to the n dimensional vector space. And the size of the circuit, which I'll denote this way, is simply the number of gates in it. Okay? And the number of gates, you might say, is the most basic resource that we might want to minimize. You know, there are other resources that one could care about, like the number of auxiliary qubits that need to be used as workspace, or the number of parallel layers of gates. Okay, but number of gates is actually a pretty robust resource. Okay, and so you so you might worry that isn't this sort of an arbitrary measure, right? What if, for example, we allowed gates that acted on 3 qubits at a time? Could that completely change the situation? Okay, well, it's one of the first observations that one can make is that as long as you only care about whether a given unitary could be realized with a polynomial number of gates or whether it requires an exponential number of gates, and you don't care about the exact count of the number of gates, but only about the asymptotic behavior, then it is very, very insensitive to choices of that kind. Okay, so for example, if we wanted 3 qubit gates, well, we could just decompose those as products of small numbers of 2 qubit gates. Okay, and there's an important result called the Solovay-Kitaev theorem that lets us control the error that's introduced when we do those sorts of simulations. Do that very well. Okay, and in fact, there are many, many alternative ways to implement quantum computation, and yet all of them seem to lead to a complexity measure that is sort of polynomially related, you could say, to the measure that I've defined here, of just the number of gates needed to prepare your state or apply your unitary transformation. Okay, there are even fairly exotic views. So that one because of topological quantum field theory, it is known that any quantum computation can be expressed as approximating the value of the Jones polynomial of some knot. Right? And yet even there, it turns out that the number of crossings needed to write down the knot whose Jones polynomial encodes your quantum computation will be polynomially related to the number of gates if you did the computation in the standard way. And that's from work by Friedman, Kitaev, and Wang, and Haranov, Jones, and Landau. Yes?
If I allow for non-unitary gates,
yes.
it's the same thing as post-selection.
Well, I mean, you could have non-unitary gates in the sense of measurements, right? Measurements, let's say, and then maybe operations conditional on the outcomes of those measurements, right? And that's realistic. That you can do as well. Now, if you want another exercise, I encourage you to show that even if you allow that resource, it doesn't let you solve any decision problems that you couldn't solve with purely unitary evolution. Okay, this is almost an engineering application of the many worlds interpretation of quantum mechanics, the statement that I just made. Okay, but that can be proven. If you want post-selection on exponentially unlikely events, then of course that is an unrealistic resource, right? To actually implement it might require repeating your quantum computation an exponential number of times until those unlikely events happened. Yeah. Oh. Sorry. Yeah. The dimension of the Hilbert space is 2 to the n, where n is the number of qubits.
The group that acts on this Hilbert, the basis of this Hilbert space is u to the power n.
Yeah.
So once we know the group, then how do you count the minimum number of elementary gates that you need?
Well, it's hard. We're going to come to that, but it is very hard in general to know what is the smallest possible circuit. We will discuss what can be said about that question, or at least what can be said about it conditional on our beliefs about complexity classes like P and NP and P-space. Yeah.
So basically, using the definition of complexity,
yes.
you can only distinguish P and exponential XP.
Well. So I didn't understand the question.
So you say you want to know the asymptotic behavior of
yes.
P in terms of n.
Right.
So if we ignore all the polynomial differences, so it seems the only difference is the polynomial and exponential.
Well, you could certainly have things intermediate between the two, like n to the log n power. Right? There are many growth rates between polynomial and exponential. Okay, and then among exponential you could have 2 to the n. Sometimes you get 2 to the square root of n. The fastest known classical algorithm for factoring, which because of the Snowden documents, we're pretty sure that the NSA is doing on 1,000-bit integers or so, takes about 2 to the cube root of n time. Okay. So yes.
So
Yeah.
then when we translate it into physics,
Uh-huh.
we can only make some qualitative statements.
Well, yeah. I mean, the more the picture that will emerge is that the more precise or quantitative the statement you want to make about circuit complexity, the further you will need to stick your neck out, the stronger the assumption that you will need to make. Okay, but I will tell you what happens if you make sort of the strongest widely believed assumptions. Okay. So let me just define some measures. Oh, so this, this sort of independence of the model, or of say what is computable by a polynomial-sized quantum circuit to sort of low-level choices about how we implement computation is often called the polynomial time Church-Turing thesis. Or let's say the quantum polynomial time Church-Turing thesis, because quantum computation itself was a counterexample to the classical version of this thesis, most of us think, right? That really is something more powerful, but as far as we know today, a quantum computer is the most powerful kind of computer based on known physics. Anything that can do something in polynomial time that a quantum computer could not do would, we think, need to be based on new physics. Okay, so let me define some measures of circuit complexity. So I'll write a script C for circuit complexity. I'll say C sub epsilon. Let's say of transforming the state psi to the state phi will simply be the minimum size of any circuit C such that C psi is within epsilon of phi, say in the L2 distance. Okay, so what can be said about this measure? Well, it is symmetric. It is equal to C sub epsilon of phi given psi. Okay, I should say that I will often suppress the dependence on epsilon when I don't care about it. Okay, and I'll just imagine that we're doing things exactly, but we can put the epsilons back in as we need to. If epsilon were equal to 0, then this is actually a distance metric on the set of quantum states, right? It satisfies the triangle inequality and so forth. I should say that when we do these transformations, I'll allow the use of ancillas. Okay, so you're allowed to take as many scratch qubits as you like, which would be initialized to the 0 state, as long as they're returned to the 0 state by the end. Okay, so it's kind of like, you're taking a test. I'll let you use scratch paper. Yeah? Well, it is very, it could be very sensitive to epsilon, right? We could have this measure be very small for a given value of epsilon, and yet when I slightly decrease epsilon, then it would jump by an exponential amount. That's true, and so we'll have to be careful about that. Yeah?
So this example that you have in physics, we sometimes call it a spin chain.
Okay,
So
sure.
In spin chain, we need to tell you that how the spins are talking to each other.
Mm-hmm.
The Hamiltonian.
Yes.
Where is the Hamiltonian coming in?
Oh, the Hamiltonian is just the log of these gates, right? So each gate, if I were to implement it in an actual device, then it's like e to the minus IHT for some h acting on that pair of qubits, and I leave it on for the requisite amount of time. That is what the experiments would actually do. In computer science, we prefer to think about discrete sets of gates. Physicists prefer Hamiltonians, but one can easily translate between the two languages. Yeah?
So in this case of quantum circuits, product
Yes.
in general, Qubit physics, do we know such a set of elementary operations exist?
Okay, that's a good question. So it depends on which Hilbert space we're dealing with. In topological quantum computation, which I mentioned, there is no natural tensor product decomposition, but there is still a notion of elementary operations, which correspond to like basic operations that you could do on a knot. Right, in that case, and then one proves non-trivially that it gives rise to the same model of quantum computation, at least if we only care about polynomial versus exponential. There's also like linear optical quantum computation, where your Hilbert space would be a Fock space, right? Given by how many photons, for example, are in each mode. And so that again is not a tensor product space, and yet with enough resources, one can prove that too becomes equivalent to the usual BQP model, under polynomial losses. Okay, good. So so what can be said about this measure? Well, it's at least 0, and I'll give it as an exercise to prove that. For any pair of n-qubit states that, this complexity of doing this transformation is going to be at most 2 to the n times some small factor, again. Okay. Okay, if I just write the complexity of a state, like C of phi, I'll just mean the complexity of transforming the all 0 initial state into that state. Okay, and if I write the complexity of an n-qubit unitary transformation, U, I'll mean the minimum size of any circuit that, when applied, implements that U. Okay, we could also put epsilons on that. To do that, we need a distance metric between unitary transformations. There is a natural choice of such metric called the diamond norm, but I won't go into it right now. Okay, so certainly one could do that. In fact, let me give it out right now as an exercise to show that for a Haar-random state, so for a completely generic n-qubit state, its circuit complexity will almost certainly be of order 2 to the n. Okay? For those who haven't seen this kind of thing, we call it a counting or dimension argument. It suffices to count how many different n-qubit states there are, every pair of which has a small inner product, versus how many different circuits are there. Let's say how many circuits are there that are, let's say, that differ by at least epsilon in their behavior. So certainly, okay, so this is actually an interesting issue. It was worth, because, the question is, can we show that circuit complexity is exponentially large in interesting cases? Well, we know how to show that almost every n-qubit state requires an exponentially large circuit to prepare it. Right? That we know how to show. I'm giving that as an exercise for you. Okay? And yet, to prove that any particular state of interest to us has exponential circuit complexity, that is much, much harder for reasons that we'll see, in fact. Yeah?
Does this assume some basic operations, the gates?
Oh, yes. So I'll allow, okay, so for this exercise, you could take let's say, fix a discrete set of gates. So there are what we call universal sets of gates. That is, gates, finite sets of gates such that by composing enough of them, one can approximate any unitary transformation on any number of qubits to any desired precision. Okay, a good example would be the so-called controlled NOT gate, which maps x comma y to x comma y plus x modulo 2. Right, so it just flips the second qubit if and only if the first qubit is 1, together with a suitable set of 1 qubit gates, such as this Hadamard gate plus, we need to get complex numbers in somewhere, so this gate. Okay, that's a good example of a universal set, and there are many others. So take a set like that. That will let you discretize your set of circuits and will make the exercise easier. Yeah?
The complexity to go from hard random state to another one.
Mm-hmm. Yeah.
How does it depend on the number of basic gates?
Oh, well, I encourage you to show that if you take 2 Haar random states, which are independent of each other, then generically the minimum circuit to get from one to the other will have size of order 2 to the n. Okay, again, by a counting argument. Okay, so again, that type of statement we know how to prove. Okay, so I can't resist mentioning one of my favorite open problems here, and maybe one more exercise. So let's define C star, so a slightly different circuit complexity measure for a given state, to be the minimum number of gates needed to prepare that state, and possibly additionally some other state that is sitting in tensor product with it. Okay, so you're allowed now to have some garbage sitting around here, right, which also gets prepared as a sort of a waste product, a byproduct of preparing phi. Okay. So now my question is there any separation or any good candidate for a separation between C and C star? Okay, I don't know of any good candidate, but neither do I know that these measures are anywhere close to each other in general. Okay, now let me give one more exercise. So show that if we have 2 n-qubit states, psi and phi, which are now orthogonal to each other, then the circuit complexity of preparing an arbitrary linear combination of psi and phi is at most twice the circuit complexity of preparing psi plus the circuit complexity of preparing phi plus order n. Okay, so we have this kind of relationship. Give you a hint, you will need to use the fact that the states are orthogonal, or at least that their inner product is bounded away from 1. If their inner product is very close to 1, then we don't expect that this statement is true in general. Okay, so you'll need to use orthogonality. You'll need to design a slightly clever circuit to do this. Okay. Excuse me? What is lambda? There's no lambda here. There's alpha, beta, what? Sorry? N. N. Okay. Sorry? Yes. Huh? Yeah? Back there? No, one can do this whole theory for mixed states, although actually I was talking to, I think, Brian Swingold, maybe, was I talking to you about this, Matt? Yeah, that there are different ways to define the circuit complexity of mixed states, which may be inequivalent to each other. For example, we could take the minimum circuit complexity of any pure state from which this mixed state arises by tracing out part of it. Okay, but we could also, consider other measures that might be different, and I think that theory sort of remains to be developed. Okay, so sorry, to speak louder.
That looks more like C star than C, right?
What does?
You unify the C state.
Uh-huh. Oh, yeah. Yeah, that may be true. Okay, so one more exercise. So let's connect this state complexity to these standard complexity classes that we talked about before. So let psi be a superposition over n-bit strings. This again is n, not lambda, like that. Now show if the function f, the wave function, is computable by a polynomial space algorithm, and if BQP were equal to PSPACE, that is, if quantum computers were able to efficiently solve every PSPACE problem, which is something that we cannot presently rule out, then the circuit complexity of preparing psi is at most polynomial in n. Okay? So, I'll give you a hint. You'll need to do some kind of recursive construction. At least that's the simplest way I know to do it, where you'll prepare each qubit one by one, conditional on the state of the previous qubits, and repeatedly using the assumptions that f is in p-space, that BQP is in p-space, and that polynomial space lets you do something over and over for an exponential number of times. Okay? So what this shows is that this sort of explains why it is so hard to unconditionally prove exponential lower bounds on the circuit complexities of explicit quantum states. Okay, and this is going to be relevant tomorrow when I tell you about, say, the work that Lenny Susskind and I did on the growth of circuit complexity in AdS CFT. This is sort of why we need to make some computational assumption in order to even get off the ground with such a result, right? Because until you prove P equals P-space, it could be that sort of every state that's sort of reasonably explicit would have a polynomial size quantum circuit to prepare it. Okay. Now, an observation that interests me enormously is that we do not know any implication analogous to this one for C of U. That is, for the circuit complexities of applying unitary transformations. Okay, so even if P were equal to P-space, right? So grant the most wild collapse of traditional complexity classes that you could possibly imagine. I do not know that it follows that, for example, decoding the Hawking radiation in the Harlow-Hayden experiment could be done efficiently, right? Or that explicit unitary transformations would then have polynomial-sized quantum circuits. The divide and conquer technique that works for preparing states does not seem to work for applying unitaries. Okay, and for this reason, it is within the realm of possibility, I think, that one could just prove unconditionally that, for example, the Harlow-Hayden experiment is hard, or that various other explicit measurements or unitary transformations would require exponentially many quantum gates to implement. Maybe one could do that without having to prove P not equal to P-space or things of that kind. That's within the realm of possibility, although at present we don't know how to do that either. Okay, so I wanted to mention we can observe that the complexity of applying unitaries, has many nice properties like like that one. What do you call that? Submultiplicativity or something. Okay, so now what we know to say is that if you're given a Boolean function f, we could define a unitary transformation u sub f. That just sort of exclusive ORs f of x into some answer register, like that. Okay? Then I'll invite you to check that in this case, the circuit complexity of applying this kind of unitary transformation is tightly related to the ordinary computational complexity of the function f. Okay, in particular, u sub f has polynomial in n circuit complexity if and only if f as a function has polynomial sized quantum circuits. Okay, so that's another exercise. Okay, but for more general use, unitaries, I don't know a relation of that type. Okay, so in the last 8 minutes or so, what I'll do is I will get started in talking about the Harlow-Hayden argument, where we will see some of these concepts play out. Okay, so Ahmed in his talks very, very nicely gave you, the basic setup of the amps or firewall paradox and the sort of basics of what Harlow and Hayden had to say about it. So I don't need to recapitulate everything that he said. Okay, but just to show you, just to briefly recall the setting, I hope you'll forgive me if instead of drawing Penrose diagrams, I just draw a cartoon. So here's a black hole. And in the amps setting, we consider sort of 3 regions. H, which is the sort of degrees of freedom that are still in the black hole, or sort of inaccessible to us if we are external observers. And then there's B, which is some Hawking photon or some quantum which is just now emerging from the black hole. And for simplicity, I'll take B to consist of a single qubit. If B is larger, it won't really change things. And then there is R, which is sort of the old Hawking radiation, quote unquote, the degrees of freedom that have already come out a while ago. Okay, and we imagine an observer, say Alice, who waits outside of the black hole for 10 to the 70th years or whatever. She has a very long grant, and she collects, she scoops up all of the Hawking radiation, routes it into her quantum computer for processing. And of course, she knew the complete initial state of the infalling matter, which was a pure state, and she knew all the relevant laws of physics. That goes without saying. Okay, and then we can now define a computational problem, which I'll call the Harlow-Hayden decoding problem. Okay. So I'll say, I'll sort of assume the quantum polynomial time Church-Turing thesis, from which it would follow that sort of all of our knowledge of the relevant laws of physics could be encapsulated by specifying what quantum circuit sort of takes the simple initial state of the infalling matter and then produces the quantum state of the Hawking radiation and the black hole at some later time, right? And here, I'm implicitly assuming that, we are able to discretize the degrees of freedom suitably. Maybe, if we believe in the finiteness of the Bekenstein-Hawking sleepwalking entropy, then, that would be an indication that maybe, we can do that in a quantum theory of gravity. But, I'm just a consultant, okay? So I'm going to leave those questions to the side, and I'm going to assume that we can model the situation in terms of a finite number of qubits. So we're given a circuit C such that, which maps the all zero state to some pure state psi that could be entangled between these three regions, R, B, and H. And now our task is to apply some unitary transformation, U sub R, to R only, which I'll assume is all that's accessible to us right now, that should have the effect of putting B and some designated qubit of R, let's say the last qubit, into a Bell pair, 0, 0 plus 1, 1 over square root of 2. Okay? So we call this decoding the entanglement, making manifest the entanglement between R and B. I will give you the promise that this is possible. Okay? So in other words, I will promise you that there is, maximal entanglement between R and B. Your challenge is to sort of unmask the entanglement by acting unitarily on R. Okay? Now, this is, and in some sense, this is what you need to get the firewall paradox going, because this is, what then, if Alice were to jump into the black hole later, would give her an actual observable violation of the monogamy of entanglement, when you combine with the entanglement that's supposed to be present between just inside and just outside the event horizon because of quantum field theory. Okay? And then, there's either a firewall or there's a breakdown of quantum mechanics, or in any case, a breakdown of no drama. Right? So, if Alice can't actually do this, then in some sense, the problem is one of her mathematical description, as opposed to an actual observable problem, you might say. Right? This is the sort of thing that you would have to do in order to make the amps problem observable. Okay? Now, now one could say, let me give you one last exercise. Prove that if this state psi RBH was Haar random, then let's say the circuit complexity of the Harlow-Hayden decoding task to abuse notation would grow exponentially with n. So sorry, I should say n is, let's say, the total entropy of the system, or the number of qubits, the total number of qubits that we are dealing with. Okay? So show that, if our pure state were Haar random, then with overwhelming probability, doing the unitary to decode this entanglement, while it is formally possible, will require an exponential number of gates. Okay, I'll give you a hint. This is yet another counting or dimension argument. Okay, the problem that Harlow and Hayden faced is that this, psi is not a Haar random state, right? In fact, we know exactly the unitary, by assumption, we know the small quantum circuit that produced this state. Okay, so I should, maybe, it's worth calling attention to the fact that everything we do in physics, in some sense, takes place in a tiny, tiny little corner of Hilbert space, right? Because, almost every state has exponential circuit complexity. Okay, that is true. And yet, if the Big Bang started in some simple and low complexity initial state, and if there's only been a limited number of operations that have happened between then and now, then all the states that we see have very, very small complexity and are therefore exceptional states, you might say. Okay, so, that's just sort of a fact of life. And so, in particular, this state of the black hole and the Hawking radiation would then be a low complexity state. And so then, now, if you go through the argument, so you can give an abstract linear algebra argument for why such a unitary use of R exists. And if you trace through that argument, you find, it gives you only an exponential upper bound on the number of gates needed to implement that unitary. Okay, so Harlow and Hayden could have just stopped there. They could have said, well, seems hard to us, we don't see how to do any better than that. Okay, but in fact, they did better, and they gave a reduction-based hardness argument. Theirs was assuming a result from my PhD thesis. What I'll do tomorrow morning is I'll give you a more streamlined argument that I came up with that eliminates the use of my PhD thesis and only requires the assumption that there is an injective one-way function that is hard to invert by a quantum computer. Okay, so we'll see how these concepts get connected, how Harlow and Hayden, how one can actually argue for the hardness of this decoding problem in a principled way, and then I'll talk about the stuff that I did with Lenny Susskind and more if we have time. All right, thanks for your attention.